an analysis of how much of that capacity is used per class, per link. If the utilization meets or within standards, you can consider yourself to be done. If they're not, the objective is the process is to go back and change one or more of those top items. You can change the topology, for example, adding capacity or adding express links, or changing the topology altogether. You can change the routing policy. You can change the QoS settings. And if you're lucky, you can change your traffic matrix, but that tends to be harder to do. Okay? And that fits within this overall process. That if you're going through it step by step, there's a section that has to do step one with getting the traffic. Step two, working through what are acceptable utilization thresholds. Step three is the part where you take the topology and those other two inputs and do the analysis. And of course, you may choose to do various optimizations either in the routing, which is in step 4, or step 5, where you're augmenting the capacity or the topology. Okay? So far, so good. Let's move on to where does the topology come from. If you remember, Clarence had listed 4 sources of input. So for the topology, for the basic infrastructure, the main 3 sources of information are listed up here. Extremely easy to get at is the ISIS or the OSPF database, the IGP database. It's cheap. You go to one router, you can get yourself a full connectivity, L3 connectivity. It's wonderful. It doesn't give you a lot of information. It often doesn't give you capacities and things like that, but you know, with that you can just get started pretty well. Most common source of information for long-term capacity planning tends to be configuration files. The configuration files do give you a heck of a lot of information, except that they give you a view of the network as it is designed, not necessarily as it's operational now. And as you'll see in future slides, there is a lot of give and take between the planning process, the engineering process, the routing process, and operational work. And you really need the 2 different views of the network, both how the network is designed and how it's operational at any given point. For the network as it's operating, of course, SNMP and show commands are the way to go. Okay? For anybody here, who wants to be embarking on doing the data gathering or working these things, the IGP topology and interface counters are quite easy to get at, and most organizations should be able to get at those relatively quickly. If you have RSVP in the network or LDP in the network, that becomes harder, and we'll go through a little bit of that as well. Same with multicast and QoS. Some of the major challenges that we're dealing with right now have to do with port channel mappings. It's difficult. It's not difficult to discover individual ports, but it's difficult to map which ports are together and which ones are the ones that will be failing together. It is difficult to get at the optical topology just because the optical equipment don't have very good automated discovery procedures, and furthermore, it's very difficult and a hassle to map how a wavelength maps to a particular L3 circuit. A lot of folks we know tend to put in the description fields, would put the description of the circuit in the optical side or vice versa to make that happen. Again, those sorts of things fall outside of things that you can say as part of a best practice. I have a tool that does it. It really has to be done in best practice within the organization. Physical infrastructure, even harder. Where is it in the particular building? What floor it's in? Which particular ducts is it going through? Another source of information that's challenging for us that's coming up is IPv6. It's not hard to discover IPv6 topology, but there are hardly any IPv6 counters, differentiated counters between IPv4 for traffic and IPv6 traffic that exist. So if you want to be doing IPv6 planning apart from IPv4, it is difficult to do. Keep that in mind. We find some of the challenges being in multi-domain services. We have folks providing mobile backhaul circuits that start in a region, go through a backbone, and go to a third region, where if you want to be providing SLAs for that whole layer 2 circuit, you have to have a notion of all the topology and all the planning processes that take place across those three, kind of being able to stitch those elements together. I don't know anybody in this room, but I'm pretty confident nobody has multi-topology routing implemented. It's relatively new, but that is very, very difficult. L2 infrastructure similarly. And last but not least, there are elements outside of the IGP layer 3 that affect the planning process. Many of you are affected by how the CDNs shift their traffic huge amounts at will, it seems, and often. And those are challenges in capacity planning that we can also discuss here as well. But I won't be immediately. Okay. So what we'll be going through here mostly will be the left-hand side. How do you get at the information and what do you do with it? And then what are the considerations to have? For the routing policy itself, again, Clarence has divided it up into how one would get at the routing under normal conditions versus routing under failures, backup paths. And what he's trying to highlight in this particular slide is the fact that, again, life is very easy with ISIS, with a simple IGP. The shortest path first algorithms are easy to simulate. It's, we already talked about how easy it is to get the information. But if you have MPLS-TE, especially dynamic MPLS-TE, where the tunnels have bandwidth and the links have reservation amounts, your planning process becomes more difficult, because it becomes difficult to predict what the actual tunnels are doing. Okay? And it's non-deterministic. It all depends on the order in which the tunnels get established. So there are some examples of this near the end, but that's something to keep in mind. The sort of planning process that works for simple IGP or static MPLS will not work for dynamic MPLS-TE. Last but not least, in this audience, I don't believe static MPLS-TEs where primary and secondary paths are provisioned ahead of time is very popular. Is that true? Anybody in this audience? Okay, one. It's a lot more prevalent amongst folks who've moved from an ATM network where this is the way of running the network. Again, planning process is very nice and easy for when one has static MPLS-TE tunnels. It just becomes more, because you set it up, it's relatively predictable. You pay the price on the operational side. You have 100 nodes. That means almost 10,000 tunnels that you have to actively manage. Okay? So as Clarence says, there's really no free lunch in there. Secondary multicast and BGP, again, there are tools like ours. Dave Wang is here from Wandel, and also shareware tools that do help in collecting this sort of information. In terms of the effect of their routing policy for backup paths on the planning process, as you can see here, the ISIS remains simple. Clarence had put in a few slides on loop-free alternates or IP fast reroute, which is an interesting, relatively new technology for having alternate backups available. That's very easy to put in, and it does not complicate the analysis too much, so we'll go across that a bit. But for the same reason that figuring out the network behavior under normal conditions was difficult with dynamic MPLS, under failure, it's doubly more difficult with dynamic MPLS. There are considerations with fast reroute and also the various versions of fast reroute. Who in this room has fast reroute implemented? One. Okay. All right, so I think we will skip much of that as well, if that's okay. Now, in terms of QoS, QoS itself is a complicated topic, but QoS policies from a planning perspective do not have to be complicated. In general, what we find is that the it is possible and desirable to come up with network-wide bandwidth allocation policies, and there'll be an example of this later on, where one takes the services that one is offering and maps them to relatively few QoS policies that may have different instantiations in the edge of the network versus the core of the network. But again, it's a policy that one sets up, and one can set up pretty much once, and that remains stable over time. So we're not going to make a big deal about automated doing a lot of manipulations of the QoS policy. We're not going to be changing those very much as part of this presentation of going about capacity planning. The most important section of the policy, especially with QoS, is basically how much headroom do you need to set aside in order to meet your SLAs. Okay, and this was this particular topic was under a lot of discussion and research, especially 10 years ago, where there was a lot of disagreement in how much headroom do you need? Do you need a lot of active management of flows in order to meet your SLAs, or can you just say, look, as long as I'm below 80%, everything is okay? I think the consensus, both in terms of research and practice, has been that as long as the link capacity is less than 80 to 90% for large links, services do okay. Is there anyone who disagrees with that at this point? I mean, I realize there are services, some military applications and some video applications where even a single drop cannot be tolerated, where you don't want to lose an iframe or the like. But generally, for most of the services for operators within NANOG, 80 to 90% seems to do okay. Okay. Well, this used to cause a lot of fights at some point. But again, we found both for folks who've been studying it from a theoretical perspective. You see the top chart there. It shows utilization on the y-axis and how much capacity is required in order to have 1 out of 1,000 packets. Only 1 out of 1,000 packets have a more than 2 milliseconds delay in getting through the queue. And as you can, it's very difficult to see, but the curve of it is around 90%, and that's, I believe, for a 2 gigabyte link. I'm not sure, but in the lower plot you can see it that all the three lines that are at the bottom, the knee of the plot is around 85%, and that's one gig link. OC12 1 gig and OC48 links at the bottom. Okay, so the bottom one is based on actual packet captures simulated through a queue, and the top one is a theoretical analysis. Okay. So basically, again, as long as the headroom that you're setting aside, under failure, under your failure policies, what you want to be looking at is around 10-20%. The services will not get affected. You don't need fancy flow management schemes to keep the services going. Okay. So that might beg the question, so what's the role of quality of service in this? If you're going to keep everything below 80 to 90%, and if you're going to plan for it, why even bother with any class of service or QoS changes? And Clarence here has put a nice example. And my summary of that example is that it's basically insurance. If you have a class of service that is either highly sensitive or highly profitable, it is nice insurance to put it in a class of its own. So an example he has is that the first class has only 2 gigabits of traffic, and there's another class of 8 gigabits of traffic. And the queues are set up that the first class can use up to 90% of that queue can use up 90% of the capacity. And the second class can use whatever is left over and just has 10% that is set aside for it. So in effect, what you get yourself is only 2 out of the 9 is used up for the first class, and you have yourself 75–85% headroom, and that basically allows for all sorts of unexpected things that happen. You might be planning for one train to derail, but now you can have one train derail and have a flood at the same time elsewhere, and this service would remain effective. Okay. It's basically just makes life, and this is perfectly reasonable, especially if the class 2 has looser SLA requirements. The two references here, one from Clarence and another one in the book that they have, go through very detailed descriptions of how to actually configure the queue settings for this sort of a setup, and I won't go into details on those. Okay. So let me stop here with the first section. I think this is the most difficult for me since Clarence had done this. The rest of them will be easier. Any questions for Clarence? All right, let's move on to traffic matrix. This is my bread and butter. Easier. So what is a traffic matrix? As part of the capacity planning, you're going to have, you're trying to move traffic around, right? A traffic or demand matrix is the notion of the load you're going to be putting on the network. And that's different depending on the application. If you're running, mostly layer 2 services and voice traffic and things like that, you can do just fine. You can do a lot of planning, barely just using core router to core router traffic matrices. Okay? Because your traffic doesn't shift very much from the outside ASs, and you can do simple planning from your ARs to the core routers. You don't need to do simulations. You can just watch for them to go above 50% and upgrade at will. But for the cases where the planning process matters, that's the core to core, all you need is core to core traffic matrix. Now, as the edges become more complicated, you might want to have AR to AR traffic matrices. On the far end, if you're doing strategic planning, long-term planning, 5-year out planning, it almost doesn't matter to have core router to core router traffic. Pop to pop traffic is just fine, because those routers are not going to be there 5 years from now anyway. And if I were to say one thing about best practice in capacity planning, start with as simple as possible. If you are really doing strategic long-term planning, just keep it to pop to pop. It's a lot more stable than router to router, any router to router traffic, and a lot more easily obtainable. And only go to CR to CR or AR to AR traffic matrices as needed. If you're running a network where you're getting a lot of traffic from the outside, if you have multiple transit providers, or very big, or a lot of CDN traffic that shifts across your endpoints of the network, at that point you want an external traffic matrix. That's not just from your routers to your routers, but from your routers to external ASs, and possibly from external ASs to other external ASs. At that point, you really need NetFlow, which Paolo will be talking about, and you've really increased the overhead and the amount of work and modeling you have to do one notch higher. That's worth keeping in mind. Now, how do you actually measure the traffic matrix? If you were to measuring the traffic matrix itself, the two common ways would be using flows or LSP information, LSP statistics. This section of the slides is also Clarence's slides, but I've modified them, and you'll see why in a second. Paolo will be talking about NetFlow quite a bit, and there's V5, V9 that we'll describe. I mean, we find that the flow statistics can be quite inaccurate at any given point in time, especially depending on the equipment you have, but are very, very useful, as you will see in a second later. For core-to-core traffic, if you have any LDP enabled for your VPN services or the like, those statistics are great. It's a lot of things to measure, and you must take account of missing values. Routers just decide not to respond, and you have to keep in mind that some router vendors only report how much traffic is transiting through a particular LDP tunnel, not just starting. But given all those caveats, it's a wonderful source of information, and one can get a good internal traffic matrix for it. Unfortunately, keep in mind, it's not per class, and there are a lot of little hassles one has to deal with. If you've gone through the process of the hassle of putting RSVP in the network, great. They've got good measurement. You can get those, and there are some people who have even gone through the trouble of putting in a full RSVP mesh with zero bandwidth, so it doesn't change the routing, just to get their traffic matrices. And they can get router-to-router traffic matrices, and even if they're a little bit odd, they get added up at a pop-to-pop level, they're perfect. Okay. So the slides that I got from Clarence said V9 is the way to go. And that was pretty much his conclusion and description. Now, for me, I'd say it's quite different. You know, somebody like Clarence who works at a router vendor, we were both standing in the same place looking at the same networks, but he's looking forward. Right? He's not looking at, like me, he's not looking at what's actually in the network now. You know, I have to deal with 7600 SUP1 cards. He's looking at, you know, this network could have ASR 99 millions in it. You know, all these things that we've done in the last 2-3 years, all these things that we're going to do. So yes, if you're looking into the future, V9 may be the way to go. But if you have a real network today that's still got equipment that you bought 5 years ago, hasn't quite been depreciated, you really cannot. You have to be flexible. You have to be able to live with what you have. The other element of it, I think, that gives someone like Clarence a slightly different vision is that when they go into a network, they do these sorts of design analyses, you know, as one-offs. They have a bunch of smart people who come in and or work with the engineers there. They work around issues, they work around troubles, they work around missing values, whatnot. They do all those things. But in my case, we're installing systems that have to stay after the engineer who was doing this gets bored and leaves. These things must be automated and live day to day and work day in, day out without a lot of hassle and without somebody watching over them. And I think last but not least, I've just been beaten into submission. You know, it's very difficult. If you've worked in any service provider, within any IT organization, it's very difficult to get things changed. You really have to live within the system. There's all sorts of good things that one can do, but most of them will not be allowed by IT in the next 12 months. So my recommendation, again, which is slightly different from Clarence's, is that, you know, start with the direct measurements. If it works, if all the processes are there, great. You're wonderful, you're done. But move towards a system where you can use link standards as a gold standard, and I'll talk through an estimation regression procedure from there, and add in additional information, be it net flow, MPLS, or whatever, LDP, whatever additional measurements that you have over time, and only as needed. Okay? Slide is slightly out of order, so I really should be describing what I mean by demand estimation. So again, let me go through it again. Do direct measurement. If it works, great. You're done. Stop. If you want to do something more, the next simplest thing to do would be to do a demand estimation, which is sometimes called tomogravity by the AT&T Labs folk. It's got different names depending on whose papers you're reading. And the demand estimation procedure is as follows. It says that you want to get an idea of how much traffic is going from router to router, let's say from A to C and A to B. But in effect, the only measurements you can make are link measurements. And imagine in this case, you're only making that link measurement between the two core routers, 6 megabits a second. The question is, how can you solve for A and B, for the traffic from A to B and the traffic from A to C, if you only have the 6 megabits measurement? And there, you can get an answer through solving that funny little linear equation at the bottom. This is a good 2-hour presentation that we've given before at NANOG, and I won't go through in details. But you can get yourself an estimate. You don't really have a notion of how much A to B is versus how much A to C is, but you know that the sum of them together is 6 megabits a second. And what you get yourself is summarized here on the left-hand side. This plot you see has known demands on the x-axis and the estimated demands through the estimation procedure on the y-axis. What you get yourself are answers that are way off. If you had estimated the demands, the AB and the BC correctly, and if you had been able to distinguish between them, all those blue dots would have come across on that 45-degree line. Okay, the numbers would have matched. And as you can see, they don't match. There's ones way out here where the known demand is considerably larger than what was estimated. Okay, so it was estimated here, it should have been more up here at the estimate. Or vice versa, the known demand is, the estimate was much higher than what you actually know to be there. But what's amazing is that for the purposes of failure analysis, just for those purposes, if you take the estimated demands that are wrong and you do failure analysis on them, you get pretty good results. And that's summarized on this right-hand plot. So the right-hand plot is failure worst-case link utilizations using the known traffic matrix on the x-axis, and on the y-axis is using the estimated ones. And those come together very, very well. And this paradox is explained by the fact that even though you can't tell the A and B's have been changed, Oakland to Baltimore versus Palo Alto to Dulles, even though you can't tell them apart, when there's a failure between the San Jose and Dulles link, both of those demands reroute together through Chicago. Okay? And that's the crucial insight. You can actually do pretty good failure planning based on link stat measurements. I wouldn't use the demands that come out of that for growth planning. I wouldn't say, well, I really believe I know how much goes from Oakland to Baltimore, and I know that's going to change by this amount. I wouldn't use it for any of those purposes. I certainly wouldn't use it for billing, but for failure analysis, that's going to get you someplace. The role of NetFlow, LSP stats, and all of those is that with relatively few of those measurements, you can bring in the known demands. Okay? You don't need to have full measurement if you have a regression estimation procedure on top of that. In this case, 1, 2, 3, 4, 5, 6, 7, about 10 very well-placed measurements did the trick. But if you can put yourself in a position where you can collect NetFlow on a few large, well-placed routers, that's wonderful. If you can get yourself just some RSVP measurements, that's wonderful. If you can do LDP, but can't do it very often, that's just enough. Again, keep in mind that interface counters really remain the most relevant and relevant statistics. All our planning procedures are based on link stats, be they 5-minute, 2-minute, whatever those link stats. And you want to use that as the gold standard. All the other sources of information need to be rolled in as a way of getting better estimates in there. And one of the examples, just to make that concrete, in one deployment, we have topology discovery done in near real time. It's keeping up with the events of the network. The LDP measurements are done, every hour. And even that's pushing it. You know, we could have done just as well with every 4-hour measurements. Not very often. It's a lot of load and strain on the routers. You just don't have to do it that often. You collect the interface measurements every 2 minutes, but then using the mathematical procedure, you can combine the two informations and get yourself pretty robust traffic matrices that are available on a 5-minute by 5-minute basis. Okay. I would actually stop right now and pass over to Paolo, unless there are any questions about either topology discovery or traffic. Okay, if not, I pass it to Paolo.
Hello, this is Paolo Lucente. As Harman said before, I'm a principal software developer at the PMSCT project, which we will be seeing a little bit in the next few slides. And today I'm contributing some 10, 11 slides, so I hope you don't really mind some 15 minutes of Italian English, so be patient. What is the PMSCT project? First of all, it is open source free GPL software initiative, and it is an IPv4, IPv6 accounting package. How you might see on this slide, so on the left-hand side you have some traffic collection methods, so lead pickup, netflow, sflow, or ulog. Of course, IPFix is missing, but IPFix is there as well. And on the other side of the PMSCT, you see some very known, some backends, so very known open source relational databases, some like MySQL, Postgre, and SQLite, but also memory tables. PMSCT can act as a NetFlow or sflow, let's say, collector. But the fact that you see also NetFlow and sflow on the right-hand side of the slide, it means that it can act also as a probe. But that's really out of discussion today. Now, in saying this, PMSCT doesn't just stay in the middle and writes to a database what is read from the network, right? So it doesn't want to be just another copy of flow tools or things like that. It really allows you to do some aggregation, so spatial and temporal aggregation, and also spatial and temporal grouping, which is something that we will see later on. And it also allows you to do some lookups based on some maps, but also very relevant to this presentation, lookups against the BGP. So, and of course you can check it out right away to the URL in the corner. PMSCT, what happened some time ago is that PMSCT was really a NetFlow sflow collector, traditional, let's say, with the features that we said, and it got added or introduced by a Quagga-based BGP daemon. So you can really imagine that as two threads that work within the same application. One is listening for NetFlow or sflow packages on one side, the other is keeping up BGP sessions with your routers. And then the two information, routing information and the telemetry information, they are joined together. Of course, that if they can be joined together. What is the basic idea how to join telemetry information with routing information is to see for the telemetry IP address, so the agent IP address, in the case of NetFlow the source IP address, or in case of sflow the agent ID, and match it against the BGP source address or the router ID. So a few features of this implementation is that one, as I said, is that it's a parallel thread within a collector. The other, very important, is that this information is never used to compute any best path route. or anything like that. So every route collected from the router is maintained separated. So you end up with per-peer BGP RIPs. And that is very important because at the end you offload a lot of calculations from the collector, which is, let's say, a central point, and you rely a lot on the best path calculation done by the routers themselves. And so why BGP at the collector, and why I ask this question is that, of course, the trend that I see, especially within the router vendors, Cisco, for example, is that especially on the software platforms, they are trying to encapsulate into the telemetry protocol, so into NetFlow, as much information as possible. So what I expect happening in the near future is that also a lot of BGP information which are not there yet today, they will be there, right? So what is my idea on that? I don't know if there is any disagreement on this, is that, you know, the telemetry protocol should report on forwarding plane, and it's a little bit suboptimal that we have a nice protocol like BGP and control plane information gets transferred over and over by NetFlow once again, right? So in my view, the optimal situation is that you get, you know, forwarding plane information from NetFlow, routing information from BGP, and then you join them together into the collector. Getting specifically to the traffic engineering, and planning, which is the main topic for today, from a standpoint of telemetry export or NetFlow export, for example, what I can see is two main models. And of course, I see two main models that they can be also combined together and create so a third model if you want. So the first one, and I think the most relevant because then it drives to a strategic solution, is that to collect from the edge routers, so the provider edge, from the provider edge routers, ingress-only measurements at edge interfaces, so the ones that are facing customers, peers, and transits. And from these routers also collect BGP information. So at the very end, you have Ps that export both, for example, NetFlow information and BGP peer with the collector. What you end up with this solution is that you will get a traffic matrix end-to-end, and it will be a unique traffic matrix with a unique view of your traffic flows, and it will be end-to-end. So it means pop-to-pop or peer BGP peer AS to BGP peer AS, or from source AS to destination AS. And so that's very interesting to do. For example, it gives a lot of information about your edges, but also what happens past your edges. So just, you know, traffic, who is pushing traffic into you, and where you are delivering traffic to. And it allows also for borders profiling. I've done some presentations in the past about PMSCCT and how you can use it in the context of peering. So that's where, for example, I speak in terms of borders profiling. And so this information, let's say, when it's coupled with IGP information or with a tool or with something that has also a knowledge about the topology of the network, then you can start also to plan and simulate for failures. And so that's very interesting, and it drives, yeah, as I said, to a strategic solution. Then you have a secondary export model, which is essentially to get still ingress-only measurement, but from PNP routers at core interfaces. So when you start doing that, you do not get a unique view of your network or of your traffic flows anymore, but you get N traffic matrices. So the beauty of this solution is that it's very basic and simple and doesn't require any routing information, because it's like you are tracking the big flows as they go through your network. But this is really a tactical solution, let's say. So the specific scenario in which I see this useful is that a problem already occurred, and then you want to know why is that, why you have some link failing 100%. So something already failed before. Now, I would like to go through two, let's say, illustrations for each of the models. So you see that the first model, yeah, you get at the very end just a single traffic matrix. So you have three flow, the red, the violet, and yellow. And you do not really know what happens within your backbone. But on the other side, you know, yeah, where traffic is coming from and going to. So that's, as I said, and you can build very well an end-to-end traffic matrices and see whether you are interested on your edge or what happens just past your edge. And just let me do a little bit digression on this traffic matrix when it comes to the source peer AS, right? Because when you, you instruct, a router to tell you about BGP information, and then you say, I want a peer AS. Of course, the source peer AS, the router, the only thing it can do is that, yeah, it will tell you based on BGP information, the traffic should have been coming, based on whatever, the traffic should come from this AS. Of course, that's very wrong because, or it's a very bad assumption. It assumes that traffic is symmetric, so it's telling you where the traffic would route that traffic, and it assumes that traffic is coming from that AS number. But of course, we all know that traffic is asymmetric most of the times, and so that's a wrong information. So what PMSCCT allows you in order to tackle the source peer AS information is to give you a map that you can update. And essentially the outcome of the solution is that you, at the very end, map AS numbers or MAC addresses to interfaces. AS numbers to interfaces, that's very good for private peering, transit, customers most of the times. Whereas, of course, you get a little bit of a problem when you get at public exchanges where, of course, you have just one interface or one logical interface and a number of BGP neighbors out of that interface. So in that case, you really need the MAC address being part of the telemetry in order to specifically determining who is pumping traffic into your backbone. Now, for who has the luxury here to run S-Flow on their devices, yeah, very good. That's how many are running S-Flow, so Brocade? Okay, I will not ask the other question. That's okay. So who has the luxury of running S-Flow in this context? Then, of course, it's sorted out because S-Flow traditionally captures the source and destination MAC addresses for flows. The problems come where on the platforms that support NetFlow, NetFlow v9 or IPFix. The funny part there is that the protocol supports very well the MAC information, MAC layer information, but vendors still tend not to have widespread support for that, especially for routed traffic. So I see that appearing more and more for switched traffic, but for routed traffic, MAC information is something that is still a little bit missing. And there was a thread right on the NANOG mailing list, which I participated very briefly, on which I was calling vendors, to move steps forward in that direction. And this is, let's say, an illustration for the second export model. And as you can see over here, you do not get anymore just a single traffic matrix. So for every flow, you can see in the square at the bottom, for every flow you get, n traffic matrices, and n is directly, related to the number of P routers that are, exporting traffic flows. And but the beauty is that you see that, for example, the red flow is touching PC, P3, P1, then it's getting out at PA. And as I said, of course, you can also match the two sort of export models together, right? So you can get the best of both worlds. Now, I would like to speak a little bit of scalability. Let's say scalability will be the main topic of the remaining slides. Of course, this is broken down in a few areas. So I will start with the BGP scalability in this sense, and then I will move toward, of course, scalability of the backend, and then finish with the traffic matrix, the scalability of the traffic matrix, whether something can be done also in that sense. So, starting with BGP peering, of course, we are saying that, the the collector should BGP peer with all the PEs, but of course you might have a lot of PEs in your network, and so it's very important to determine upfront what would be the memory footprint required. So something like the megabyte per peer or something like that. So PMSCCT at the very beginning was employing just a very simple algorithm by which every BGP table that was got from the routers was stored separately. And of course you can see that's the red line, a very linear growth. So 50 megabyte per peer. So you have 100 peers, and then you calculate how much memory you need in that sense. But then, of course, that was not scaling very well. Getting past also the 100 or 150 peers, of course, was posing an issue, like you need a lot of memory. And so what happened is that I come up with a different sort of algorithm, but which essentially, and that's the blue line that you see at the bottom, that essentially starts converging on the 18 megs per peer, and essentially it just has one BGP table with all the seeing prefixes, let's say, from all the BGP peers, and then of course there is a sort of layer of virtualization, so there is some metadata saying from which peer I've seen that prefix. So there is this sort of two-step algorithm. And so what you can see, the result of that, is that for 500p routers, then you have a consumption of roughly 9 gig of memory. Of course, how this is calculated, you can see at the top of this illustration, which is with 500,000 IPv4 routes, 50K IPv6 routes, and a 64-bit executable. So, moving to the backend, I would say that the main idea behind PMSCCT over the time was that you need some sort of aggregation, because of writing every microflow to the disk, it's something not scalable, right? So yeah, you can still do that because disk maybe are very cheap and things like that, but then when you need to build a report, then that's where it will hit. And so why doing then the aggregation later on? You do it right away, and that really drives to a project-driven approach to NetFlow. So just which is a little bit something which is not done in a lot of companies. So in a lot of organizations, what I verify is that NetFlow, why you are collecting NetFlow, yeah, I'm doing that just for the sake of, right? One day it will be useful for something, so storing everything. But I think that's a little bit wrong. If you do not need NetFlow, then yeah, you should not collect it. And if you need it, then you have a very clear ideas on what you want to do. And if that's the case, then you can take a more project-oriented approach to NetFlow, and so start aggregating data up front and not just let it go on your disks forever, and then you never know if you can count on that data, yes or no. So the microflow approach is okay, but it's good for development, network development, for lab and things like that. But for a production network, for operators that really are seeking for information out of it, I mean, I don't see much sense in doing that. But of course, if anybody disagrees with that, we can have discussion later on or whatever. So what you can do, for example, in PMSCCT is, as I said, temporal and spatial aggregation. So, for example, you can define an aggregate with the number of primitives that you see over there, peer source IP, peer destination IP, peer and whatever, and then do SQL history 5 minutes. So essentially, you not only are saying that I want just a subset of the primitives from the routing plane or from the telemetry plane, let's say, but you can also build it in time bins. So 5 minutes, 10 minutes, 1 hour, whatever. That will build a data tuple like the one that you see over there defined in SQL. And at the very end, you can do also some temporal grouping. So if you see at the clock over there, you can create SQL tables per hour, for example. So what you have is some aggregated data on the spatial side and aggregated data on the temporal side, and then you can still group it by hour or by day or by whatever you want. Still on the scalability, so as you can do some temporal grouping, you can do also spatial grouping. So you have your network and you chop up your networks into different SQL tables, right? So what I imagine over here is that, for example, you have regions, so what I call it here cluster 1, 2, 3, and 4, and you assign that to different SQL tables, and that can be also in addition to the temporal grouping. So it's not either or, but you can do it even both of them. What is the rationale behind doing the grouping and the aggregation? The rationale is that SQL is a very beautiful language, but so very powerful. You can get a lot of information with it. It's standardized, so you can get also people in your organization which is just out of the university, they will know about SQL, so it's not something new for them, it's not something proprietary. But the downside of relational databases is that if tables then become very, very big, then they are not manageable anymore unless you have plenty of resources. So in order to plan the resources better, it's what I'm presenting is a number of divide et impera approaches by which essentially you can really divide the data as you prefer to keep the SQL table very small and manageable. And still on scalability, I mean, a single collector might not fit it all, like a single PC running PMSSD might not fit it all because, don't know, for example, you have memory issue or CPU issue and things like that. So once again, the divide et impera approach is very valid. So what you can do is really to assign routers to collectors, and then you can assign collectors to databases, or you can also cluster the database. That's really up to you. So also matrices can get rather big, so can we do anything about it? My take is that yes, so we can. So first of all is that we can keep smaller routers out of the equation. So what I see is that a lot of organizations, they are interested into the top flows or high-speed customers. So 1 gig interfaces, 10 gig interfaces, 100 gig interfaces, and things like that. Of course, there is still plenty of legacy around, so serial interfaces, Cisco 7200, Cisco 10K, just to make some examples. So in my opinion, those small routers can be kept out of the equation. You don't really need an overview onto the small flows or the routers that can't really contribute something which is painful for your backbone. And of course, because nowadays it's very common to use also modular chassis, so Juniper MX or Cisco 7600, ASR, and things like that, then of course you start getting also the low-speed serial customers also on these other platforms. So doing the same algorithm as before, I mean, you can just not include those interfaces into the equation, so do not enable the export on those interfaces. Then the other advice maybe is to focus on the relevant traffic direction. So for example, upstream if you are a CDN, or downstream if you are a service provider. So that's what in linear algebra they would call the triangular matrix. So essentially you just, instead of focusing on the full square, you just focus on a direction or on the half matrix that you really think it's useful to yourself. Of course, there is still some players out there, like IP carriers or people that tend to put, both CDN and eyeballs on the same network, that of course, yeah, they still need the full matrix, and that's it. And of course, the last advice is to increase the sampling rate, right? This is something I will not comment a lot, SQL. I don't want to come at now and comment on SQL. But let's say this is just for who is more or less familiar with SQL to see how, at the very end, a query to get the traffic out of the database would look like, right? So I think it's very logical, and it's just for your reference for the future. And because, let's say, time is never enough, and I had to skim through a number of topics which are very interesting, which are, for example, the auto-discovery and automation, because as Arman also was saying, I mean, without auto-discovery and automation, you don't go anywhere. And also the entities on the provider IP address space, because we spoke a lot about BGP, but you also lend a lot of your IP addresses to your customers, for example, so what can you do in that case? And then, other stuff, together with some presentation about the specific case of peering and some quick start guides and whatever. So I would like to leave you with all of these references that are publicly available, and make your way through them, and if there is any questions, you pay me a beer and we are friends. So thanks very much. And any question now? Good, thanks.
All right, well, Paolo is too modest to compare PMA CCT with any other tools, but I will do that for him. In the last 10 years we've been working on this in this area. PMA CCT has really stood out in terms of being the most scalable, usable, and affordable way to go. It's very difficult, we found, to do to have any of the existing systems, especially the commercial ones, where you can enable it on all of your edge routers at any reasonable cost, and also at any reasonable maintainability. Paolo is concerned that it all doesn't fit on one collector, right? But imagine if your collection was limited, 5 routers to one collector. The amount of hassle and scale of requiring to maintain that is considerably larger. And of course, the price is right. It's just a beer. So, and again, we're working with Paolo for a lot of the integration to just make a lot of the discovery and just make it less and less hassle to get the information out and pass it to the planning component. Okay, we're actually doing well on time. To the third portion of this talk. As a reminder, we're talking about planning. As I said before, planning is really one part of a comprehensive traffic management. Decisions one makes on how much capacity to put in place, how to control routing, strategically over, to configure routing primary and secondary, versus operationally being able to notice congestion and just move traffic around. All of those really go hand in hand as part of a single system. What I'm going to be really concentrating here is that top portion that's you can see with the oval, and talking a little bit about how with the practice of planning, one can get out of some common and wasteful topologies. So specifically, building core topologies that are built in ladder shape or ring shape are just wasteful. Because for each of those things, you're setting aside a whole unit of capacity as backup for every unit that you're using for your primary. It can be expensive. Furthermore, with the rings and the other ones, it's just a hassle, because again, if you have to maintain similar capacities across the whole network, and cost-wise, it's quite big. So there's a comparison between 1-to-1 saving versus 2-to-1 protection. And the idea is that if you can configure your network in the ladder, for example, where imagine just only one of the links is being used to carry the primary. When that fails, if the other toolings can be used as backup, that rather implies that the first link could go up to 66% utilization without, each link could go up to 66 without causing congestion under failure modes. And it's a big difference, right? If for every $100 million, it's nice to be able to save 15 to 20 million in practice. Supposedly you should be saving more, but it's that 15 to 20% is quite useful. Similarly, if you want to get out of a ring topology and be adding express links here and there, 10 to 20% savings are common. But again, nothing is free. Once you go out of a simple ring or a ladder, you have to pay for it in terms of beefing up your planning processes. Okay? And just jump directly to that. So as soon as you're out of the ladder or the ring, link statistics are not enough. Right? You need to be able to look at the failure modes of your network. And that's where your planning folks need to understand your topologies. They need to understand what sort of routing is possible, what affects it. And similarly, the operations folk need to be able to know, hey, well, how do I move things around if I really must? And those lines get blurred. I'm not going to spend a huge amount of time on this just to make sure that we are able to finish up in about 20 minutes. But again, the idea is to be able to take the traffic matrix from before, scale it up as appropriate, be able to do the simulation analysis, and have the utilization thresholds be looked at under worst case traffic. Okay? So that's the what if analysis that says, hey, look, if under failure I'm still less than the magic 80%, with the anticipated growth, I'm fine, I'm done. Okay? Secondly, if you find yourself you're not done, that you're not being there, it is entirely worthwhile to be looking at modifying the topology. If there's a large amount of traffic going from Chicago to Washington, there's really no reason for it to be going through Detroit. Why not just add a direct link in there? And that both to improve the protection and to cut some port costs. And last but not least, the idea of being able to separate the traffic so that you're you're making per service source of planning becomes again very powerful, because what it means is that if you have some traffic which you absolutely don't mind being dropped every now and then, under big failure at peak time, you could conceivably, and there are people who've known to do that, say, look, my acceptable utilization limit is 125%, 130%. It's okay. They're paying me $3 a megabit. It's okay. And that again drives the cost quite a bit. Now, the counterpart to changing the capacity and changing the topology of the network is to be able to do some network optimization to make the best use of the capacity that is already there. Okay. Again, Clarence's nice quote is network engineering is the process of manipulating your network to suit your traffic, versus traffic engineering, which we're moving to now, which is manipulating your traffic to suit your network. We're finding that there is a desire to be able to do traffic engineering, but a definite fear in terms of the complexities involved. And so because of that, most of the slides on this have to do with alternatives to what has been touted as traffic engineering for the last 10 years, which is RSVPTE. Or MPLS-TE. And the questions that Clarence wants everybody to be able to ask themselves is, which approach am I going to use, IGP or MPLS? Am I going to be doing this strategically? Am I going to be laying out a whole routing for normal and failure conditions, or just tactically let things get congested as need be, as it happens, and be able to mitigate that congestion afterwards. I'll jump over the questions and go directly to the fish, which I'm sure everybody is sick of seeing. Has anyone not seen this picture? Or has everyone seen this picture, I assume, over time? Again, it's the classic picture that says you want to get some traffic from the left-hand side to the right-hand side. The shortest path is across the northern path. And you find yourself getting congested. You do want to utilize the southern route, but how do you do it? And 10 years ago, people would see this picture and they would say, well, you can change some of the IGP metrics, then all the traffic switches over and, mayhem strikes, so let's make sure to put in tunnels, and then you can peel off the traffic, piece by piece, so to say. Okay. And again here, the main thing I want to emphasize is the fact that people do, even in the year 2011, still continue to manipulate their IGP metrics as a way of traffic engineering. It is, in my experience, still the most common way. It has its place. Yes, it is possible to be shifting traffic if you're doing it blindly, to be shifting traffic a lot. But a lot of the time, most folks are using, creating equal cost paths, and things just don't go crazy. Okay? I mean, there are limitations for traffic engineering itself, and there are limitations on traffic engineering using the IGP. And again, keep in mind, traffic engineering is not going to create capacity. If you have a bottleneck, you have a bottleneck. If your policy is to be resilient to single failures, and you have a router with just 2 uplinks, you must add capacity at that point, at some point. But in the cases that you do have the room, this is the slide I was just talking to about with changing the metrics in order to create equal cost. With lots of references in between. Again, I'm going to walk you through an example of a network. It's not a made-up network. It was existing data, real data, to get a sense for how just manipulating metrics can bring down utilizations quite a bit. In this case, again, this is the US, the northern routes tend to be faster. In this case, you had a lot of traffic going from peering points in Chicago to eyeballs on the East Coast, and a lot of them going across the top path under normal, or if the link between Chicago and Detroit up here were to fail, a lot of the traffic shifting to this southern middle route. Okay. There is, again, no reason to be completely afraid of this. There are established procedures, tools in place that allow one to change the metrics such that where you start with lots of congestion under worst case traffic before, you can get yourself a huge way off, from 120% normal utilization to 72, or bringing it down by almost a factor of 3rd under failure. These are not crazy numbers. This is what takes place normally. So if you want to do T, if you do want to get out of the one-to-one protection, this is quite possible. It's done on a day-to-day basis, and you do not have to make an investment in RSVP if you don't want to. Okay. This is a bit old, from 2002, but we looked at a set of real networks, comparing the different procedures, manipulating metrics, not doing anything, just leaving the metrics as they are, manipulating the metrics versus manipulating RSVP paths. And we're finding that if your objective is to bringing down maximum utilization, Of course, not doing anything. Sorry, this is, that's right. Not doing anything, which is, say the red is the display-based metrics, just delay-based metrics. You're quite a bit far off from the optimal, but often the green, which is the optimized metrics, are quite good. It's not as good as explicitly manipulating your RSVP traffic. Right, in some cases, like here, it's 90 to 100% off. But a lot of people find that trade-off to be worthwhile. That you pay a 10% trade-off, but you save yourself a huge amount of hassle and changing procedures. I have examples of that. Let me just jump to it here. So this was presented at one of the NANOGs in Las Vegas, I believe, where again this comparison was being made, and they could see that introducing tunnels would decrease the worst case failure utilization, that's this axis here, and would decrease it under normal. It was a bit lower, but manipulating the metrics, even though it was a bit higher, was good enough. So let's not add to the complexity of the network if we don't need to. Now again, this is not for everybody. If you're in a situation where your network traffic changes a huge amount, is extremely dynamic, as is the case for some of the more enterprise-like networks, where it's not a huge aggregation of individual customers that you're dealing with. In those cases, using dynamic tunnels is actually quite appropriate and maybe the only way to go. For those cases, tunnel sizing is really key. How do you keep the tunnel bandwidth in sync with the actual traffic that's going in it? And I highly recommend anybody who's thinking about introducing that to do an analysis of their tunnel bandwidth setting procedure against the traffic profile that they see. What we've found consistently is that if you use auto bandwidth with the straight procedures as they come out of the box, you'll find yourself that you're either often behind or ahead of the traffic curve. So you can see here, these are the bandwidth lag. You can see that you're setting it too high and you're catching up to making it lower over time, but the traffic has already changed and is increasing. At each of these places, if you're here, you're in a position where your network is potentially rejecting tunnels needlessly. And at these points here, you're risking congestion for absolutely no reason at all. Because your tunnels believe a certain amount of bandwidth going through them, but in actuality there's more. So really for dynamic MPLS, the key is to make sure that the tunnel sizing is done well. We're finding that it's a relatively small number of people who are using auto bandwidth, and they've really had to tweak it to get it right. Offline sizing seems to be more prevalent, where relatively periodically there's an external procedure that looks at all the data and makes it already sees ahead and sets the tunnel based on what is expected to be coming in the next 4 hours or the next 24 hours, and that gives one a lot more stable network, and you bypass the need for having readjustments that take place often and can be running ahead or behind. Okay. So this example here, we have only about 15 minutes left. I will jump over a lot of the TE discussions. I think in the past few years, we have had many discussions on this topic. I highly recommend any of the presentations my colleague Thomas Telka has given on this topic. Those cover the choice between where to put the mesh, how to make sure that your own routers are not sending traffic to different tunnels under failure. That if an edge router is sending traffic to a particular core router, that it continues to do that instead of sloshing the traffic around elsewhere under failure. And he has a good case study on the use of dynamic MPLC from Global Crossing, 2004. So I will skip over those. Okay, but just jump to the conclusion. Basically, metric T is viable. It does have its limitations. If you're going to use, if you need dynamic MPLS tunnels, make sure that tunnel sizing issues are taken care of and traffic sloshing is taken in place. Explicit tunnels are in use, especially amongst folks who are transitioning from ATM, but it takes a lot of overhead. Okay. Any questions on this topic before going on? Nope. Before we move to the next section, who has heard of loop-free alternates or IP fast routes? Wow. It's much fewer than I thought. Okay. So again, in 2001, a lot of discussions was about fast route. You have a failure in your network. Let's put in fast route tunnels that will very quickly transition traffic from a link to an alternate path that bypasses that link. And a lot of the discussion was how do you set up these alternate paths and whatnot. Again, given the issues and complexities of maintaining all the various fast route ones, there's been a desire to have the routers just figure out an alternate by themselves and send things along the alternate path. In this case, if you look at a source of the traffic being S and the destination being D1, if the normal best path is through router F, what the routers do with loop-free alternates is to look at every other neighbor other than the one whose failure you're looking at, and see if S were to send its traffic to C, would C just send it back to S for the destination D1, or would C forward to someplace else that would go on? Similar question for E. So the router by itself, without needing to communicate with anybody else, creates an alternates table. For each prefix, in addition to the best path, it creates a list of alternates that it believes do not send the traffic back to it. And then it looks at, well, which of the alternates do I send it on? Of course, prefer primary over secondary. If the backup path has the lowest metric, send it that one. Presumably that's the least delay penalty. Line card disjointness, node disjointness, plus a bunch of options to fine-tune things, which he doesn't recommend you use after all, but you never know, it becomes handy. The benefits is it's simple. Doesn't require any IETF changes. You don't have to worry about interoperability. If it works, it just works. Okay. And that's beautiful. Less than 50 milliseconds, no tunnels, no maintenance. It's a little bit harder to plan. Again, that's why I'm here, I guess. But in terms of hassles, it's very low on that part. Okay. The main constraints on it are that it's topology dependent. If you have a ring and you're sitting at the top of the ring and want to be sending something to a node that's at 3 o'clock, if this link between 12 and 1 o'clock fails, if you send it to the one that's at 11 o'clock, it is just going to be sending it back to you. Right? So for a lot of topologies, there are no loop-free alternates available. So, it's definitely not a panacea. The beauty of it is that for a lot of preset edge topologies, you can work out the metrics such that you're guaranteed loop-free alternates. Okay? And so Clarence has put together this slide as a way of a decision tree for saying when loop-free alternate is viable. Along the top branch, if your target convergence is to be less than 1 second, you can set your you can tune your timers and all to be able to have IGP pass convergence, and there are lots and lots of how-tos on that. And then you can put in this loop-free alternates as a bonus. If you're targeting less than 50 milliseconds, and you're on the edge, that's the sweet spot. There are well-established guidelines, you can follow them and get loop-free alternates in place. For the backbone, you need to do some analysis to see when loop-free alternates are applicable, and in the cases that are not, and only in those cases do you need to bother with something heavier like TE fast reroute. And they have done some studies on it, which I cannot claim to be able to describe well, but that the 5 topologies were well protected. About 95% of the actual traffic was well protected on those. And like I said before, there's a ton of edge topologies, common edge topologies, where they have worked out the metrics, so you can just turn it on. And another link to some studies on IP fast reroute. Okay. And as I said at the beginning, we're going to skip this part. Let me just walk you through 3 minutes for an example of the design exercise. A full design exercise in 3 minutes. Okay. This is a fictional example based on a real case. Mobile backbone with 6 already defined core sites predefined, and many feeder sites, only 3 of which are shown here: Kiel, Cologne, and Bonn. And again, the objective was to have a cost-effective, low-delay solution, and that meets the projected traffic matrix. The optical design rules here were similar to many folks, is that the core links should go over the shortest delay. That the primary core link should go over the shortest delay. And it should be diverse, right? You don't want to have a single optical failure bring down multiple core links. For the remote PEs, it would be homed into the closest PE first, and secondarily into the next closest PE, as long as it's diverse. Okay? And then the IP design rules were, as you can see here, 2 PE routers in each site, 2 PEs in each site, and a bunch of edge routers where the traffic is actually being sourced, being brought into the network from the media gateways. Okay? So these are relatively cheap, and they're being used as aggregation devices. The optical network itself, again, I've been told this is pretty realistic for the German optical network. It's a little bit difficult to see the geographic layout, so there's a schematic layout presented here. Okay. Lots of rings, nothing terribly unusual. What's interesting is that if you were to route these core links that are displayed here over the optical in the shortest delay possible, you will get yourself optical segments that house multiple core links, right? One here between Frankfurt and Cologne, and another one between Frankfurt and Darmstadt. And what that means is that a single optical failure, a single SRLG, a single thing, could bring down 2 of the major core links, which is undesirable. So it's not so bad. What you can do is, instead of routing Düsseldorf to Frankfurt over this shortest path, you can go slightly longer through Kassel and Erfurt. And similarly for Cologne to Stuttgart, remember it was going through Darmstadt. Now have it go through Bonn, we speed in months, and then to Stuttgart. And you have yourself nice diverse paths. Okay. Relatively quick, so you get yourself an initial topology built. That's 2 minutes for the core. Then for the PEs, some of them is easy for the remote nodes. Something like Kiel, the closest is Hamburg, second closest is Düsseldorf. They're diverse, you're done. For Bonn, it's a little bit more difficult because the closest PE is Düsseldorf, right here, but second closest is Frankfurt, and so Bonn is here. And that would not be diverse. You see, this would be common failure here. Right? So you look at the next closest, and that's Stuttgart. So that becomes where it gets homed into. And okay, right now within 3 minutes you have yourself a design. You have the traffic matrix, you have the design. You can do the simulation analysis and size the links initially such that they're green under normal and less than, that magic 80-85% under failure. Okay? So you're done with your capacity planning portion. You can use one of the made add-ons or many of these exist to look at how much LFA coverage you have. And you notice that indeed in the core, there's a lot of places where you do not have LFA coverage. But in the edge, you do. And you can do a little bit of metric optimization insofar as if you do create ECMP paths in the core, that also brings up your loop-free alternate coverage, right? ECMP is the poor man's LFA, after all. And there you have it. It took 4 minutes, but you have a full network design and capacity analysis in about 4 minutes. Okay. So I will conclude. We've tried to make a case for how capacity planning and describing how it's essential for ensuring SLAs. Okay? If you want to have SLAs within reasonable cost, it is worthwhile to put in a more robust capacity planning process. The router vendors have their parts in making sure that the infrastructure is there to provide the information. Planning tools like us work to automate the discovery, the traffic matrix, doing the simulation and optimization. But one of the things I've really tried to point out here is that it is so much easier to stick to what you have than to try to change anything in a service provider network. It is difficult, and I'm very sympathetic for that. For these sorts of changes to take place, for any company or any network infrastructure provider to go beyond Excel and what's easy, to move into something that is that gives you that 15 to 20% savings, that is more flexible. It is going to take effort, and ultimately it's you guys that have to put together the vision for the management that this is something we do want to do, and it takes time and effort to put those things through. And I encourage you to do that. All right, I think we're done. We even have a few minutes for questions or comments. It's okay, it's okay. Okay, if there are no questions, comments, we can be done 50 seconds early. Thank you very, very much.